will still be coming in. Cam won't be in though, so that's that one. Hey, welcome to Coffee Compiler Club. We're here today to talk about compilers and language runtimes and whether or not JVMs can survive stack overflows and out of memories and whatever other things cross our heads. You're being recorded. You'll be on YouTube within a couple hours generally. And Mark had a burning question he wanted to fire, so fire away.
Yeah, so it's on Java, related to ThreadLocal random, intrinsics, and safe points.
Oh,
so
okay.
Get all of those things mixed together. So I've brought ThreadLocal random up here before. I love it. It's so amazingly fast. But I recently saw an issue with it in production where we had tons of threads slowing down in ThreadLocal random. And we saw this with async profiler, which is not supposed to have a safe point bias. But we saw these threads sitting at a safe point in ThreadLocal random, which also felt weird that ThreadLocal random has a safe point, but it clearly should because it has an uncounted loop. My understanding is all uncounted loops have to have a safe point. And I was trying to understand the overhead of a safe point outside of if we have a garbage collection pending, because it seems like my argument is we must have some secondary issue or primary issue that's causing us to have a lot of waiting GCs for the safe point to actually mean anything, but still, it was a little surprising to me that safe point is there to begin with.
Yeah, so I'd have to look at the code, tell you where the safe point shows up. If you're an uncounted loop, you'll have a safe point. If there's no, if your async profiler only gives you ticks at a safe point, it's not a safe point, it's safe point biased.
I tossed the code into the chat, but yeah, it's async profiler is not supposed to have a safe point bias.
Okay, then it shouldn't be it should be reporting at machine code instructions and not at safe points.
Right. It reported it was the instruction, not the instruction it was at, but it showed us I'm waiting in the C code called : safe point, which was interesting. I'd never actually seen that show up before in a profiler. Okay,
so your code has clearly got a loop with a weird bounds, so that's going to have a safe point in it.
Right, and that'll be on the back edge of the loop.
Somewhere in the original bytecodes, it will be somewhere in the loop, probably on the back edge. After C2 gets done with it, the loop may have been rolled or unrolled or partially peeled or any number of things, and so the safe point might effectively have migrated. You also have mix32 and next seed, which you didn't put the code in for, which if they're small enough, they get inline. But what I'm coming around to is, why would you stop at a safe point in this loop preferentially unless you're in it all the time? And you're getting ticked here because you're running this a billion times a second on 20 threads. Yep. And then any safe point at all happens to hit this one spot because that's the only spot.
Yeah, the change. So the code that's pasted here is directly from the JDK. This is ThreadLocal random circa Java, I think 11.
Yeah,
but we added some code that happened to call this ThreadLocal random with a value of 100, where we should have used the power of 2, but we didn't. So that makes it go into this odd loop, right? Which is uncounted, right? Yeah, so it's I'm going to keep running until I get a random number that I'm happy with, right? So who knows how many iterations it goes through.
Oh, geez, wait, what does it do? It takes you a mod of your bound.
Yeah, I mean, the comment 2 lines up is important, right? It's trying to drop overrepresented candidates. But basically, it's doing the classic mod to fit you into your bound and then checking, it looks like basically checking if you would overflow from the original unbounded.
Theodore, if you got a duck, that I can also poke at mix32 and next seed, make sure they should just inline.
Yeah, those are simple. Here, I'll throw in next seed.
Special.
No, it's just a put long.
I mean, if instead of 100 you put 3 in as the worst case scenario of a non-power of 2 number, you have to get less than by re-rolling the dice. So assuming that next seed is a re-roll of dice,
maybe share
giving you
screen
a number up to a billion.
Yeah, I can. I'll share since I have this.
Oh, let me throw share up here. Yeah, try it now. I guess what I'm claiming is the code I'm reading here says if you use a non-power of 2, you are punished.
Yes, yes.
And you should not ever, you have to increase your font now. Oh God, it's black and white too.
Oh, well, that's
Yeah,
not
no,
good.
no,
Let's see.
increase your font.
Yeah, I need to go to
I
presentation
know you have
mode
to
and
go
then
find it. Yeah, fine. Okay, right. So then you say, you mod
yeah, like
down pretty hard.
huge penalty for going here, right?
Right, right.
So U is the original random number that was, no, R was the original random number, right? Then just truncated the high bit so we were
Is
non-negative,
zero. Yeah,
right?
positive,
And
right.
M was just bound -1, right? So it's like, if we're gonna roll over, right? Because then
Yeah.
this is just the like corrected one. So like if we would roll over, if we're very close to the edge of max int, then like try again, which seems like it shouldn't be that likely that you'd actually cycle through here many times unless you had stupidly high bounds either.
Huh.
Right. So it's like, I assume in most cases you don't even do the second round here, but I'm assuming you're still paying the safe point penalty, which it's like, this is very,
No. Safe point has no safe point penalty. Ought to be 1 clock of a load compare branch compared to everything else you got going on here will be, well, and plus it'll force some things to stay alive. U changes, M is loop invariant, R changes, they'll have to all be represented by something in registers. Still not a bad count. A bunch of things have to sit in registers, but they would anyhow. Save point should not add any extra overhead to the loop other than a load compare branch.
okay. But when the safe point bit is actually set, then we're going to hold the thread, right? Because we hit a safe point, right? That's the,
well, like the thread will stop in the middle of the loop and go to other things. I mean, I hold the thread.
well, I guess I was thinking in terms of like, if there was a pending GC.
Yeah,
right.
Yeah. You'll stop at that save point and your profiler will pick it up.
Okay.
Because
what other things would cause it to stop other than GC? Because I'm wondering, like, clearly we were stopping here more often than was expected, right? So
okay,
the save point's a problem, but it's more that because
right.
it actually was a positive save point.
Subclass your random and override next int with your favorite one plus a global counter. And run again and count your bumps per second.
Okay.
As a way to make sure you're in fact executing this loop far more times than you think. So the surface presentation is you get way more counts here per second than you expect.
Yep.
Here you go. Your next seed code, which you threw in there, go pull up next seed. I'm highly suspicious already. Yeah, what the hell is capital U?
Unsafe.
Oh, unsafe. Okay. All right. I always use the word. It's fine. I was thinking you were hitting some sort of weird locking table. Thread.current thread should be
free, right?
Yes, should be a cheaty free thing.
Yeah, and no safe point check on that, right? It's like, it's not J and I, it's just like absolute freeness.
Yeah, it's like well on Azul it's shift a register and mod it or and it or whatever and you're done. It's really cheap. On OpenJDK, I don't know what it is, but I thought it was also fairly cheap. I think they reserved like GS or one of the weird segment registers and just moved it.
Right.
Which, okay, fine. That was not going to do some. Oh, you could have cache line ping pong, but only if your thread locals were in a shared hash table or something.
This is operating against memories in the thread object, right? So there should be no, and I think it's padded as well. Like, yeah, this is the magic of ThreadLocal random.
They have to not be the thread T, which is the current thread object. So, sorry, current thread. Well, no, it should be there. Current thread at the bytecode and JVM level, there is a notion of a thread ID or a thread local thing, which is only known to the JVM. That's one clock cycle effectively to get at. There is a mirror object that's in the Java heap this is going to fetch from. So he actually probably takes some funny register and does a game on it in a couple clocks, 1, 2, and now has the base of a storage area that should be thread local and well spaced from other threads. Then he goes and loads a Java object and does an offset game or something and stores into it or whatever put on what are the get the seed, add something, store the seed, but what is you putting into, where's your offset?
I think
What
that
is
would be
go find me you.
says-
Is you really just unsafe, or is it like an
Yeah, there
object
you go.
of some kind?
It's unsafe.
Okay. Oh, seed is your field offset. All right, fine. No, that makes sense. Okay, so mystery solved.
where did C come in?
Seed is, I'm looking for the offset.
Oh, seed is the
random
offset.
number
Yeah,
seed,
yeah.
but that's a field name offset, which is not what I
Right.
would have guessed. So fine.
Right.
So that's the offset I was looking for. You have a base of a Java object, you have an offset, you load from the offset, you add gamma, you store the offset. Fine. No, this should not do anything in the load compare store with whatever gamma is, which I assume is another
Special number.
modest thing. Yeah, right. It's some random, hey, bump my
Oh,
seed
yeah.
by a fixed weird
Yeah,
amount.
we're adding, right?
Yeah, we're adding. Yes. You're doing an
Yeah.
incrementally with a large number.
Yeah,
Which
into uncontended space.
in theory should be uncontended space. Yeah, I
Let's
don't
see.
know why you'd be hitting safe points there. In the land of Azul, I could go tell you why you're hitting safe points there.
Right. So here's the seed, and it's padded as well.
And
right.
contended
So
means go pad you out.
yeah, with like 128 bytes on either side.
Yes. Okay, fine.
Yeah. So I assume that's free. Mix 32.
Hopefully that gamma is co-prime with the space.
Yeah, there's a weird game that you could have where gamma is forcing you to re-hammer something with the bound game. If you had a weird seed and a weird gamma, you get stuck in a loop. That would be a bad RNG option, which I wouldn't have guessed. So I'm back around to.
But as long as gamma is co-prime with the size of the ring, it should be fine.
Say again?
As long as gamma is co-prime with the size of the ring, it should be fine.
Yeah, and I mean, it looks like it, like really. And then I assume mix 32 is just a bit shuffle, which you were going to show, and there's your bit shuffle. Yeah, fine. Okay, so
magic numbers, right? So
yeah.
It's like this. This is the cost, right? Like none of what we actually do in the loop is expensive, but having the loop.
Yeah, having the loop means if you think the loop trips, it's written as a loop, but even that wouldn't trick C2. C2 ought to peel that loop one iteration at least. And then if it doesn't, if it only rarely takes the back edge, you'd have a straight line piece of code.
Okay, right.
You pass the test that says you're less than 0 and you'd walk away. So
yeah, I was trying to like infer that from some profiling, like the speed difference from this path versus this path. And it was like, it's like a 15x difference between those two. And then I replaced this with my own counted loop, forcing it, seeing how many iterations of this loop I had to do before I got back to that 16x. And it was about 4 iterations. So my rough guess is that any call into this is not just a single iteration. Although I thought that was surprising because with this, it seemed like, and I was using, I don't remember what number I was using, but it was a low bound. I wouldn't have thought I would be tripping it at all.
Right. Well, the other thing here is if you're calling in here a bajillion times, you have a mod and you have a bunch of math. So at least 3 multiplies with large constants. That whole pile compared to a single AND mask is going to be 15x. One pass through here could easily be 15x that AND mask.
Yeah. Okay. Yeah. Right. Well, we did all that crazy math up here to begin with, right? It's just the additional passes are effectively calling this method again, right? So this is the only extra.
Yeah, right. That extra is, it's a div. As far as I know, is still 30 clocks, not pipelined.
Yeah, I was actually surprised when I tested that as well, because at first I looked at this like, why isn't this whole thing just a mod? And it came. Let's see. I have a.
It's not a mod because you get bad RNGs out of it.
Where did I get it?
Pretty good random PGR has a discussion about why they do the bounds thing. And
yeah, I was trying to figure that out too. Is the cost when I just added in the mod and like got rid of the loop? Don't highlight it. It's still like my JMH test came out at sub nanosecond, which is the same thing I got for. Actually, it ended up cheaper than a power of 2 bound, which avoided the mod entirely. It's as if mod is no longer an expensive instruction,
Okay.
which I was happy to see that, but maybe JMH is.
Suppose mod is 30 clocks, but pipelines with other ops as long as you don't mod twice. And also your branch is highly predictable and you don't need the result for a while because you do a mod, you do a test, he predicts the branch, he's waiting for the mod, and the mod comes back and the branch is good, and he just ran forward and he buried all the latency under the future work. I have no idea.
Okay.
You know, I haven't heard any news that mod was more or less cheaper, but it could have happened. I wasn't paying close attention.
Okay, but let's see. To get back to my original question.
Yeah.
So
why are you
the things that
pointing
will cause you to get stopped at a safe point is if there's a pending GC, and what are some of the other things that would?
Yeah, right. So on Azul, I could name the names. On OpenJDK, I have worst options for naming names. There's shit like you have a bias lock, you're always taking, and someone's not unwinding it properly, so he has to unwind it the hard way every time. Your GC, for whatever reason, wants to keep crawling this particular stack, and your young gens are really cheap, so he's crawling it a lot, but that still seems pretty high. Your safe point.
So on the bias lock one, so if the thread that called the random number generator was holding a biased lock, that would cause it to stop at the safe point.
And if another thread wants to take the same lock, so when you hold a biased lock, you lie about you owning it.
Yep.
And then you don't bother to check whether you should lock or unlock. You just assume it's locked by you permanently, and everybody cheats on the lock semantics around this particular lock. That's the whole goal. Another thread wants it. Do you own it? You don't know. So you have to safe point yourself and go crawl your stack and count lock from the JVM state.
So is this when some other thread wants to take out a lock that's currently held in bias mode, it effectively sets some indicator on the thread that owns it that says, please figure out what you're doing and give me the lock?
Yeah. Please figure out how much you own it. And if you own it, really, you lock it the normal way. And then when you unlock it, I'll get a chance. And if you don't own it, you'll just unlock it and wake me up and I'll go grab the lock and carry on.
Okay, so I do know that in the case where we saw this, the threads that were stuck in this also were holding a monitor, right? And I assume other threads were trying to acquire that monitor. So even if we assume the thread owned it properly, that's going to still make it, the fact that it held it when it hit a safe point is going to make that safe point more meaningful, make it do all sorts of analysis to figure out whether it needs to do anything.
Right, but these are all things that should happen once. The lock should flip. Okay, here is an OpenJDK potential bug. I'm making up a bug on OpenJDK. I have no clue. He does the bias thing. He triggers the slow path. He says you need to let go of the lock. At the next unlock, he lets it go, and some other thread acquires. But the JITted code still has the biased lock notion. So when the new guy acquires, he immediately moves it into a biased lock state. Now he runs holding the lock indefinitely, and the next guy comes and says, I need this lock again, and he has to get unbiased again. Like, as soon as you fail on a biased lock, you need to rejit the code. If you haven't rejitted the code, the next guy who got the lock, like, you let it go the hard way, you took expensive time, you let it go. Yeah. Next guy grabbed it, he just biases it again. And you endlessly bias lock fight. And bias lock fights are expensive, relatively speaking.
So you're saying that it won't remove the bias locking from that code path. It'll just endlessly get stuck in that fight.
Yeah, I'm saying a potential bug that the OpenJDK may have.
I see. Right.
I don't know.
Yep.
Right. I know this kind of behavior was things that we looked at Azul, and we were in the middle of engineering when we knew this could be a problem, and we sorted all that out. And I redid all the heroic optimization tracking at Azul, and it looks nothing like what happens in the OpenJDK. And I had a very easy time of adding heroic bit here saying it's a heroic optimization to take this lock bias, but it looks good. And then if somebody fails, the bit tracks and says, don't do it. And you rejit it. And he says, oh, this lock failed heroically last time on bias. Don't bias it again and just do the normal code. And then if that's the case, you really have a bunch of threads fighting over a lock now. So you still have lock contention possibility.
Right.
Yeah.
Right. Okay, cool. That helps a lot, because I was looking at it like there must be a new source of excessive GC that is triggering this, but no, the bias locking actually sounds like a much better candidate based on what I saw.
I really made that up, and you dogpiled in on it, and I'm okay with that. There are other reasons it could be here, but that one's an easy. You throw the flag. You say minus XX minus bias locking.
Yep. Yeah, true. My suggestion to them was still like, let's just use a power of 2 bound and avoid all sorts of stuff.
Right. That one looks cheaper too. I'm curious as to, but I guess you're right. He shouldn't back edge very often there. And C2 should profile and know that, and he should unroll the loop, and the first round should predict branch exit loop correctly, and blah, 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 and it all should run fast.
Yeah, it's still, I mean, there's a noticeable performance difference between the two code paths here. Like I said, like 16x. Like, so I was like, how often do you actually care that much about your bound? Like, just round it up to the next power of 2.
Well, I don't know what his bound is about. Like if I'm rolling,
it was,
I'm rolling a 4-sided dice. I'm rolling a 4-sided dice.
Yeah. This was a like 1% of the time we want to go this route. I'm like, okay, well, 1 out of 128 is close enough to 1%. Like,
yeah, fine. And then Lynn threw out add log safe point, which is a flag I hadn't seen before. But if you're doing bias locking safe points, they should show up in such a log dump.
Cool. Okay. Well, thank you for letting me hijack the first 20 minutes.
No, we're always desperate for opening comments, so
there you go.
It's all good.
Thanks,
now we have to come up with a new topic.
Well, I have a somewhat related question. I want to have a bunch of randomness in my libraries, like one that's evenly distributed, one is like mostly true random, and like whatever other types.
Yeah.
But I don't know what is public domain, because I specifically want one that I can give to everyone that doesn't require a license to follow.
Right.
So I have no idea what is good and in the public domain.
When I was last asking this question, H2O, I grabbed PGR, pretty good random. And it had a very generous license. I don't remember what it was, but we could use it in our open source product. Now, open source wasn't GPL, it was Apache v2. So they were compatible with Apache v2 back then. There's lots of these. These you should be able to find.
So we should just read the H2O code and hope that they did their background check right?
No, you should go grab PGR, because then you can blame PGR and not H2O. Like I wouldn't drag H2O in here. I'm just saying I used pretty good random at H2O. There are other ones we looked at, like Machine Twister and stuff, that came with good licenses, but they were also fairly more expensive. And PGR was like, gave a good answer, let us skip ahead in the random stream so we could throw out pseudo random numbers across a cluster at no cost, basically, and have a totally repeatable distributed calculation using pseudo random numbers. So you can go look and see all the comments on the PGR website page. I'm gonna go find it. I didn't find the license yet.
I think I saw 2 types of benchmarks that measured how good of random several things are.
Yeah, there's a bunch of good tests available. Those are also generally very public domain.
Yeah, but I kind of got lazy on what I should include, because I figure if I'm going to offer like a secondary library, then I could just look into it. But I still really want at least one random in my primary library.
Oh yeah. And adding the distributions on top of that are pretty easy. I threw the link in the document. I say PC. I kept saying PGR because that's what I said at the time, but I'm getting now PCG. But I think that's the one I was looking at. They've changed their website and extended it and stuff. I'm going to be,
So how did the math guys want you to test that you hadn't biased your random?
Who wants me to test that?
How did the math guys want you to test that?
Oh, they have a bunch of
testing random is subtle.
No, right, but this is a well understood problem to the math. I guess I lived in the math community for like H2 years, like 5 years. But these are well known, well understood tests. A lot of common, fast, easy generators like anything it does shifts and mods and ands and adds and multiplies all fall down on certain things, but they're fast and they're generally good enough. If I'm selling a math package to mathematicians and data scientists, I have to have better than that, and that's why I went to a more complicated thing. But you know, you grab any of the linear congruential, that's what I was trying to say, linear congruential ones as a first cut and walk away. Those are like totally, completely free, you know, Creative Commons, no license, anything free. Yeah, here's John Cook. He's one of these guys that does a lot of these things, how to test. Yeah, that's a good one. Throw that in the docs there, Matt. Or did you already? I did already. Not yet. I'm going to click through and look here. But John Cook did a bunch of stuff, and we grabbed his numerical algorithms for a lot of things. And including we might have been testing with his stuff too, because we tested that machine twister, and we tested an easy linear congruential one also. And we picked up, I want to say, it was called PGR, and I typed PGR into Google and I got this PCG just random. So I'm assuming it's the same thing. Fine. It was fast. It was simple.
What's the quality on that
Kind
twister?
of matched Mark's algorithm empirically. Like I looked at it. I think instead of doing mod, they had a less than test directly against overflow, and they forced you down with a. Like the mod didn't come immediately. They had some other clever way to do it, but maybe mod was the right answer, especially if it's actually cheap these days.
Do you happen to remember what the quality of the twister algorithm was?
Oh, all of these are very good, unless you are a hardcore data scientist doing something very sensitive to the RNG properties. These are all fine. Like, of all our clients, maybe one, maybe two cared about the RNG quality. As soon as you got something slightly sensible, you're well past. You know, I'm moving pseudo-random to just spray my data around the cluster to avoid hot spotting of hot blocks. Okay, any linear congruential random is way better, good enough, and that's super cheap, so I don't care. If I'm running Marco, what the hell? What's the damn simulation here? Not Marco Polo simulation. Fuck it, I don't remember now. There's all these simulations where you do a lot of RNGs, and those
Monte Carlo.
Sensitive. Say again.
Monte Carlo simulation.
Monte Carlo. Jeez,
I'm forever going to call it a Marco Polo from now on.
It was, yes. It's too much beer last night. My brain has been fried. Here,
Yeah,
Matt
speaking of which, where's Cam?
for another one. Oh, he says machine twister is one to avoid. Yeah, it was expensive for sure, and maybe what quality wasn't that great. I remember PGR came out pretty well.
Has anyone looked at the Sobel generators? Those are supposed to be good for MCMC because of their coverage.
Throw a link in. These are like things to stare at, not online.
So Sobel is a quasi-random number generator, so it's a little bit different.
Yes.
Because it is fully deterministic. It is specifically if you would like to have a simulation with a very uniformly spread random numbers, exactly like in Monte Carlo. But I wouldn't use it as a general purpose randomness source because it is not designed for that. It's
Yes.
specifically designed for coverage.
Gotcha. So he gets all the different corners of the space as opposed to re-rolling random.
Exactly, and it solves the problem that the uniform pseudo-random number generators generally cluster. You would see those irregularities and they result in less coverage and thus slower convergence rate for things like Monte Carlo integration routines. So you may be able to improve that. But there is a lot of caveats, especially when you go to higher dimensions. It is harder and harder to obtain good quality quasi-random numbers. Also, I haven't looked closely into that, but some of the algorithms may have patents on them. So that's something to be aware of if you would like to put them in production.
I would, yes, stare at your license first. And the PCG first level page is not giving me a license. I'm very surprised.
Has anyone messed with RD random? It's a CPU instruction.
Okay. PCG random, I just found it's Apache v2.
Livo, listen, just if you want to implement something yourself, just use X or Shift and rotate. It's called Zoroshiro. You can implement it in a few lines of code, and then you don't have to worry about the license. Just read the algorithmic description and try those few lines yourself. I think that's the simplest way to go.
Yeah, and then later.
Is there a way for Is there a way for me to test it that I did it correct?
No, it's not important. You
And
can
there are
argue-
some quality tests. You can run one of them. Just Google for randomness testing, or just go for that link I posted. And
Yeah.
Okay.
At the state of your current count of users and libraries, it doesn't matter. Put a thing in that does random, put a little comment saying, this one sucks, but it'll do the job for now. Put the easiest thing you can put in that passes whatever free license there is, and walk away. When you have 1,000 users and people are jumping up and down, go get a better one.
In one place in my library, I actually use a read timestamp as a source of random, but that's only because I don't actually need random. I just need a unique number.
Yeah, right. Yeah, fine.
Do you all have favorite sources of entropy for when you're seeding things?
Oh, I do the same thing. Nanotime on Java.
Because I know for a long time Java just used the tick counter as its, I need to get some random.
It was
Because
milliseconds.
the time since boot is kind of random.
Yeah. Oh, current time millis is what they used, I believe, forever and a day.
I know when Google started doing a lot of machine learning stuff and they needed lots of random very quickly, they would just turn on a bunch of cameras in a dark room.
Really? Okay.
Yeah, if you get a cell phone camera and you attach that to the motherboard, it's basically just measuring heat in the low bits anyway. So you can get 40 megabits of random every 60 times a second or whatever.
Okay.
Wow.
If you're doing machine learning and you need a lot of random really fast, just turn on a camera and only take the low bits of the pixels. You get some decent random.
Okay.
That might be better than a room full of lava lamps.
I like that one.
My
though.
guess is it is identical to the room full of lava lamps, that it turns out that a camera pointed at lava lamps is a good source of random, and a camera pointed at literally anything is a good source of random. Including with the cap on.
Yeah, yes, exactly. Paint the lens and turn the camera on and right, and amplify black and see what you get. All right. Are we done beating random to death?
But yeah, I know that Google had some problems when they tried to initialize their random states for large language models. The tick counter does not give you megabytes worth of random a second.
Not per second. No. Well, that was the whole pseudo random. You rolled forward every thread. If you're doing linear congruential, every thread takes 2 or 3 clocks to produce their new random version. Just that linear congruential isn't super random. It's decent. It's not super random, which maybe if you're doing tons of deep learning, you need a better random source. Yeah, it could be.
I don't remember what the problem was with doing stochastic gradient descent with not very good random.
Oh, any of the not very good randoms on an algorithm that expects true random gets issues. They migrate sideways, arrange, because the RNG keeps repeating bits at a certain range, and you're modding it down to what you need the range to be. And so your high order bits or your low order bits are always the same. And so you skew sideways, not randomly, and you never, your Roomba is vacuuming your room at random. And if he's not actually random, he'll get stuck in patterns and not ever visit one corner of the room.
for stochastic gradient descent, the algorithm probably would have less chance of converging to the minimum. I mean, just
Right.
think about stochastic gradient descent as a way to approximate gradient descent. By stochasticity, you are basically sampling. And if you have the random number generator that is worse quality, then your sampling is of worse quality. Thus, the correctness argument for the asymptotic convergence of the stochastic gradient descent falls apart.
Oh, I didn't think about that one. I just knew it would suck because I'm certain I've tried that at H2O. I didn't think
Right.
about the convergence algorithm.
It's kind of like a law of, think of computing the expected value of a random number by using arithmetic average, right? You can think of a law of large numbers, and this average should eventually converge. Now, what you're doing when you have stochastic gradient descent, you are computing a sort of an average where you are sampling from your batch size only a select examples. And if your sampling is screwed up because your algorithm is screwed up, you aren't going to be able to make this argument work. because you no longer have something that is approximation to the expected value.
Okay. Yeah.
I got a new topic. All right, no one wants to stay on random. All right. So I was convinced that I need to be able to talk about my language for about 10 minutes, just using voice. And after writing it down, I just realized that I went into too much detail, and I actually don't know what typical people would want to know about a new language. The only thing I know is that they want it to be easy. They might want to know why it's easy to like understand or to deal with,
Easy
and they want to know the
varies by
performance.
person as well. Everyone wants it to be easy, but no one will agree on what easy means.
Easy is
Yeah,
not
so-
simple.
Yeah, I was
Yeah,
just
simple helps a
wondering,
lot.
yeah, what would people want to know? It's easy, or how it might be simple, the performance, and like what else? Like, do people want like easy to generate some XML out of it? Like, I have no idea what people care about.
I think the main thing people want is like a selling pitch. So like, why should they use your language over the
What is the difference
other
between your
languages?
language and the language I'm using?
I don't think they really care about, because if you look at like C# versus Python versus Java, they all want like some specific library or to be able to do something. But I don't know what a significant amount of people want to be able to do.
A library is actually a good argument. If you have killer library ecosystem like Python, then you are actually more relevant as a language if you don't. That's just true.
I think I should mention that. Yeah, I gotta figure out what a library selling point could be.
You know, I'm going to start by saying I don't got libraries yet. This is for people who want to play until I get libraries. I'm not going to pretend I got them.
Right. But when I think about some of the languages, there were real thesis statements behind languages. When Java was being adopted, people were very clear of write once, run everywhere was a major thesis statement.
Yeah.
And stack traces are better than segfaults was a major thesis statement.
Yes. And garbage collection was better than malloc. Yes. Or free, better than free. I think these were all major original statements. Java 5 became threading is well defined on all hardware platforms. What it means to have two threads talk through shared memory is a well-defined thing. Followed by, and here's a bunch of libraries for doing cross-thread communication safe things like concurrent hash tables and concurrent reader-writer locks and all that kind of stuff.
Did Python have anything? I only know batteries included.
Yeah, Python's now got libraries off the wazoo.
Hey, at least it's not Perl.
So say that again.
Oh,
Matt.
Perl was pretty popular.
He's
Why
proposing
was,
the thesis statement for Python of at least it's not Perl.
Yes. Yeah, Python thesis statement was, Pythonic is good looking code. They had and compared to Perl, absolutely.
I managed to avoid Perl except for one job, but I don't know how Perl got popular.
I used it back in the day because it did all this system crap in a programmable language. It wasn't shell scripting. It was better than shell scripting. And
Yeah.
you could do file IO, you could do multi-threads, you could cross our shells to remote servers and do shit.
So
And
it's like
with
a better
CGI bin,
shell.
it was good at integrating with the web.
Oh, there you go. That was pretty
Perl
much-
was a good early way to get something accessible either through HTTP or through Gopher.
Oh, interesting.
It was
And
garbage
it was
collector.
richer than awk. Eventually you had the moment where you're like, I wish awk had more features, and Perl
Yes,
was
yes.
richer awk.
I did a few times use it as a better awk. Yeah. Sorry, Levo, you were trying to say something?
No. I just remember that it was garbage collected, because when you said system programming, I was like, is that correct? Because I couldn't remember that.
When I say systems programming here, I meant interacting with the system. Like the shell, you needed a way to talk to the system, and you didn't get your talking. I wanted to rsync all these directories and delete these other log files and have a rollover and blah, 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 and had 27 things I had to do to get my production system running. Okay. I hand did them 10, 20 times for a month. I'm tired of it. I need a script. Okay, the shell scripting for that sucked. So you reached for Perl as a better shell script, if you will. I did. And I knew plenty of people did. Reach for Perl as a better shell script.
Yeah.
And that's what I meant by systems programming. It wasn't writing the Linux kernel. It was using the OS to make my production setup go.
I never actually sat down to learn Python, but that's what I use Python for.
Okay. Yeah. You can use Python these days. In fact, I would not reach for Perl under almost any circumstance.
Yeah.
Having a REPL that, in real time lets you screw around with things and then make mistakes and correct them and go, that's a big deal. And, Perl gave me a REPL over the shell that was programmable in a better way. Well, so does Python these days, and it has for a while. And Java really didn't ever get to the point where it had a REPL that you could hack against, and that kind of sucked.
But I certainly
Java.
see AA as positioned more to compete with C and Java and C# than to compete with Python and Perl and Bash.
I totally expect to be a REPL from day one, square one. Whether or not that turns it into a Bash thing, I don't know. I mean, it's type safe, but I'm hoping it has so low annotation overheads that you would just use it like a type safe REPL. That would be one of my goals. Whether or not that actually happens. Okay, short AA update. I spent this last week adding memory and side effects to Hindley-Milner. Going okay. I'm running out of things to have to do integration. This is on the main code, not on the theory side. So I'm running out of things to go do here. A week ago, I hit about my first quarter of all tests, and they're all the basic shitty things that have to work, including overloads and Hindley-Milner done on recursive cyclic types and functions and stuff. That was all working. And then I added memory, and I'll get back to almost back to where I was, but with side effects properly done. And then I think I'm on to, I don't know what happens after that. I think I have to fix my type parser to support type functions if I want to have better ways to distinguish type variables in complicated types. So there's something happening there at some point down the road. So progress, grind. And Cameron's not here because he's at Crazy Bob's wake. And we went out to dinner last night and had a good time. And I had too much beer. It's all good. All right, somebody else's turn. Aaron, where are you at on your projects? Or can you talk about them anymore? Oh, he's got.
Yeah, so my project is still trying to build decentralized interpreter things. A lot of TypeScript is being ripped out and being replaced with Rust because it turns out that it is surprisingly difficult to get predictable performance out of TypeScript.
Yeah, I can buy that.
It turns out having concepts like I would like to pass a reference and not necessarily make a copy of this thing is really nice.
Or you can't do that in TypeScript? You're getting copies all the time?
Yeah, we particularly everything we tried to do with string processing, where it's like, can we not make 9 copies of this string while we read something in and process it?
Yeah.
And it turns out that the answer in JavaScript land is sometimes no.
Wow. Okay.
And it's like, it's actually something like 40 times faster to call split on a string than it is to try and actually walk the string and pull pieces out of it using the ranging features.
Okay. Yeah. Yes. Okay. Yes. The other way around Java.
I got 2 questions for Aaron.
That's your death.
Maybe you should answer both these questions at the same time. So the first one is, I'm assuming that Go, C#, and Java, they're not going to give you the performance you want. And then my other question is, why not use Zig if you're going with something that people are not very familiar with? Because I find that readability is very, very important, and Zig is pretty readable if you can't use like C#.
You gonna answer that, Aaron?
But
can-
my understanding of Zig is that it does very well in circumstances where you would have to call unsafe a lot. And we are trying to
It's true.
stay away from the unsafe stuff. So
Very
where
good
I think
reason.
Zig is probably has some real advantages over Rust where you call unsafe a lot. I don't know that it has that many advantages over Rust where you actually play Rust's games with the borrow checker and get it to be happy.
I was
And
just
we
more
want
concerned about
that
readability.
increased amount of safety in exchange for a very pedantic compiler.
I would have thought that the answer would have been more like, I can hire Rust compilers, a dime a dozen, and there's a large, well-supported audience, or I mean, a collection of people building and working and hacking on Rust, and I'm a big company. And if I touch a tiny language with a tiny code base, I'm not going to ever let it be on my high profit main money-making path, because that makes my life depend on Zig before, you know, and Zig
Yeah.
living and breathing.
I have a lot of faith in the Rust community to keep going.
Yeah, exactly. You know, I think Rust is solid, and it's a good choice for anybody. Whereas I think Zig would work for me, perhaps, because I don't have any money involved. But if I was a billion-dollar company, I wouldn't touch Zig in my main code base in any way, shape, or form.
So as for the Go, C#, Java,
Performance.
my guess is that each of those, so Java is probably an exception, because the thing about Java is there's a lot of tooling out there to tell you about the performance of your Java code. So even if the maximum possible speed we were going to get out of Java is less than the maximum possible speed we were going to get out of Rust, the fact that there are tools that are very good at telling you where you did something stupid in Java, I think you can get to a happy place much faster in Java, and the JVM is really powerful. So if the particular developers we had lying around had a lot of experience in Java, I would have said, yes, you probably could accomplish all of the things that we are trying to accomplish in Java.
That's a good answer.
The particular developers that we had lying around, we actually had more years of Rust experience than Java experience in our group.
I guess
Wow.
that's a fine answer. Should I use Zig, or should I use Rust, or should I use Python? Well, I have 100 Rust programmers lying around. I've got
This is the
20
first
Java
time I heard
programmers
that.
and no Zig programmers.
And I think that is going to be increasingly true when you try to do database-y stuff. That the database community never really bought into Java for whatever reason.
Yeah. I did meet the guy who did the JVM that's in the Oracle database for running basically stored procedures in Java last night. So that was fun.
Really? I bet he's an interesting person to talk to.
Rob Lee did some, he's not there now doing that, but that was his first job out of grad school.
But that has been my experience when you try and find people who really understand how to do databases. And if you want to do a distributed database, you need people who understand databases, is that the most of the expertise there is C++, and increasingly people are getting familiar with Rust.
Yes,
And
I thought
we didn't want to use C++, so we ended up using Rust.
Yeah, I don't blame anyone for not wanting to use C++. I'm a little bit surprised about the people not using Java for databases, because Apache, Cassandra, and like all those stuff, the distributed databases, seem to all depend on Java. So I was pretty surprised to hear you say that.
The older database crowd always started from C-like environments, and they were always used to touching bare metal directly forever and a day. So blocks on disk and slabs of memory and right ahead journaling, logging things, they all had a very low level feel to everything they did, because their work was performance critical in that era. And you fast forward some time, and that feeling, just like AAA shooters, that feeling is still very strong in those domains. They are used to the low level control of the bare metal, and that's, you know, part of their job is to convert your query into a bare metal thing.
I would have thought that just using Java and the cache would be fast enough to beat the disk IO.
A younger generation came along and said, hey, I don't know, MongoDB or Hazelcast or whatever. There's a bunch of guys who did things where they rethunk how you looked at these problems. And I know a bunch of people reached for Java.
It's worth mentioning that the new engine in Apache Spark has been rewritten in C++. It's called Photon, and it has been rewritten for very good reasons that have to do with performance, including I/O performance. Remember that in Linux, when you want to use something like the new I/O Uring system, that's generally exposed through C APIs, and interoperability with C APIs from Java is terrible for latency. And you want to use it for the latency as pretty much the reason the entry. So I think, especially if you're trying to optimize the I/O subsystem, you will probably want to use some language that gives you direct access to that. Although Java may have an improved store with Project Panama, but that's still a work in progress.
So I know at H2O, we had no trouble slamming all I/O devices to their hardware limits. There was never a problem just maxing out the hardware. There's batch reads and batch writes, but we could, no trouble, distributed, scale out, batch read terabytes, and all disks were at their max limit.
How often did you have to call unsafe or generate JVM code to do it?
The generate code was one time, every time we saw a new Java object that had to cross the wire. So if you wanted to pass a foo object you just made up and hand it to the other guy on the other side, they first did a handshake one time to say, this is how we compress a foo object. And then everyone knew and you didn't have to make that code anymore.
Oh, I was thinking more, how often were you generating JVM bytecode rather than compiling Java code?
Oh, no. You almost always had an application that was Java code. You linked in H2O as a library and you called it with your ML favorite bits. When the H2O platform read and they talked cross cluster, they generated bytecode strictly for the serialization and then they were done. Unsafe was used rarely to do misaligned loads and stores on certain compression strategies, but that was it. So like we could fill
I was going to say, I've never tried to do something in Java like read a bunch of delta compressed variable size ints that
you're always
I imagine
totally
are aligned somewhat terribly.
Right, you're always bound by the speed of memory and you're reading sequentially through memory. So the x86 is prefetching the crap out of things. You're still completely bound by the speed of memory. The delta compression is trivial to decompress in registers. That's all your cost is the memory bandwidth. It's not the delta compression itself because the cache miss gives you bazillion cycles to go recover, to go finish the decompression on the fly. We could always max out memory bandwidth reading and writing as we passed things about. Like the serializer code would then JIT, and that JIT in code would hit memory bandwidth speeds to pack and unpack NIO buffers into Java objects. So there would be a copy, but only the one from NIO buffer into Java object.
So I've heard you use the phrase several times when you're decompressing the delta encoded integers, decompress it only in registers.
Yeah.
That's how you keep things cheap.
Yeah.
What do you need to do to convince Java that these things should live in registers?
There were a bunch of things we did to make life go fast. Definitely one of them was don't load decompressed data through your memory bandwidth, through your memory bus, because that's your bottleneck on memory bandwidth. Or we were bottlenecked on memory bandwidth. That was an obvious, easy bottleneck. So the fix was that you read compressed data into registers and then you decompressed. And you picked compression strategies that you could decompress in registers easily. And you never ever read the decompressed version except the initial time which you pulled it off disk and you compressed it. After it was compressed, you never read it again, decompressed.
My understanding is off. So are you compressing is the compressed data in the registers or you're just decompressing with the registers?
It is both in the registers because I did a load of a cache line worth of data into a register. I then took some set of bytes according to the compression strategy. An easy one would be 2 byte compressed ints, and I need a shift scale add. So I got a pile of Linux timestamps. I have done a measurement on these million Linux timestamps. They sequentially increment from each other, but the deltas between them are never more than 65K. So I put a base down of a few billion. I add a 2-byte offset to that base. So when I want to go read the thing, I've read some cache line. I have a base sitting in a register that I read when I started reading this million set of timestamps. I take my cache line and I grabbed 2 bytes and I shifted the register for the next cache line for the next one, and I have a 2-byte thing. And maybe I did a scale on it, a shift, probably a multiply, and I add it to the base. That's my timestamp. So an add and a shift, or an add and a scale or a multiply, 1-2 clocks tops. I've now decompressed. So I didn't write it that way. I wrote it as for I equals 1 to n, and grab from a chunk dot at this element number, and the chunk said take the I, mod it by, or just subtract off the base for this chunk, and load 2 bytes. And the JVM unrolled that loop 4 times and said, don't load 2 bytes, and 2 bytes and 2 bytes, load 8 bytes and shift and mask, because the JVM will totally do that. That's just part of loop unrolling. It's what loop unrolling is about. So the end result was I would one load of 4 bytes, 8 bytes, and x86 says he loaded 8 bytes, and then the next 8 bytes, and the next 8 bytes. I prefetch, and he starts prefetching already on me. And now I got 8 bytes, and I said, the JIT under the hood said take 2 off with a and mask shift, blah blah blah. Oh, now what do I do? Well, the decompression strategy is add 4, shift once, add this bajillion base. I got the number. And now I do my math. Now I have my timestamp. I do whatever I do the math on. So the decompression was usually 1 to 2 clocks, plus your memory bandwidth overhead costs, which were always much higher. Not always.
I'm curious here, what you just said. If you could get better incoming bandwidth from arithmetic encoding, would you pay for it in the deconstruction of the frequencies?
We always did. We broke the data up in these chunks of 1,000 to 1,000,000 elements, and we ran 20 compression strats on them. Generally ran the math to decide what compression strat would give you the best compression. And then we picked one of 20 odd strats for this chunk, and the next chunk got its own answer. Now, was one of those an arithmetic encoding? There were a lot of Huffman encoding things. There were a lot of run length encoding, a lot of delta encoding, a lot of bias offset scaling math. I said there were like 20 of them picked. Could we have thrown in some sort of arithmetic encoding? Yes. Did we specifically have one? I don't think so.
I've been shocked how well run length encoding works.
I'm sorry? Oh.
Run length encoding is so simple, and there's so many data sets that it just does ridiculously well on.
Absolutely. Absolutely. And part of this—
Here's your dictionary. It's got 8 things in it. I'm going to compress it down to 3 bits, and 90% of the time, it's always the same one.
Mm-hmm. No. And these things would stack too. So if we looked at a data set and it had a large collection, it had 2 weird numbers, but one was 90% and one was 10%. We, Huffman encode our way forward, or we run length encode and said, you're this, and then you skip, and then you're this, and then you skip, and you just put the skip bytes in, and your first one and the second guy, and the first one and the second guy, and you're just skipping whatever. And all those kind of strats are in there, and you pick up on them. Also, if we had to do a not available number, that was a thing that most data sets supported. We would set aside one of the encoding choices for the not available. And that varied by chunk to chunk according to the actual values that did show up in the chunk. So it was no extra overhead to be not available other than one state encoding out of your choices. And if it was the hot state encoding and most things are not available, you would be the default for the run length encoding, and you would skip all the not availables with your run length, and then you would say, and then here's some actual stuff, and then you would run length skip the next 100 guys because they're all not available, and so on and so forth.
Yeah,
so once you get
frequently been impressed at the degree to which nullable int64s are not actually any more expensive to store than int64s. Because there's always a number that you're not using if you have 30 megabyte chunks of int64s.
That's right. That's right. There's always a number you're not using. So you can always throw one of the states in there, and that's exactly what we did. So yeah. And once you got 1 or 2 strats in there, it was easy to add more. And somebody would come up with a data set, and you'd be looking at whatever, and you're like, holy shit, we're doing a really bad job here. What's this data look like really? And you look at the data, like, oh fuck, we should do blah blah blah. And you just add another compression strata in. And that would be a day's worth of work, maybe. You know, some engineer would pile in and say, oh geez, let's do this guy. And after a while, you know, you got most of them most of the time, and you had hard time sorting out how to get the next data set get significantly interestingly smaller than what you were doing already. And
Yeah.
didn't care.
And it turns out if you're building a database, there's enough time series data in the world that these strategies are just hugely compressing.
Hugely profitable. Yeah. So on one of the shift scale add ones for timestamps, I didn't say it quite right. You knew that you were advancing time as a monotonically increasing. So you picked an average line that you can make an integer multiple for the scale on the line, and you would just take the offset from the start times the rate on the line, and that was the center point, and you did delta from there. So for I equals 1 to n, you take I times the scale factor.
Yeah, we used to call that double delta encoding.
Okay, yeah, fine. And yeah, and compression.
We had the delta off the last one, and then we had the whole slant of what the average delta was, and then the delta off the average.
Right. And then the actual cost to compress just like shrinks down. Yeah.
This is
that works really well if you are measuring a number of GCs that have happened in a time series database.
Oh, wait,
GCs that have happened since you started your JVM. It's basically a straight line, and all the data is these tiny little jitter off of that linearly growing line.
I was looking at people's giant IoT sensor data things, right? They would have timestamp and sensor value. Sensor values were in this 9 and 12-bit range, but they had 64 bits of Linux timestamps since the epoch.
Oh yeah, if you take
together.
a temperature reading that's a floating point number and a time since 1970 in nanoseconds.
Right.
You can really compress those things.
Yes, that's
Turns out the temperature doesn't actually change that much in half a second.
Yes. Anyhow, some good performance gains to be had by doing stupid compression things. Sorry, Leo, you were trying to say something.
Yeah, this is reminding me of a video I saw on graphics decompression. It's 2-bit graphics using Pokemon. Like it was actually using the Pokemon game. Yeah, I threw that link in the
you said 2-bit graphics?
The documents. Yeah,
black and
so
white.
the Game Boy, no, it's black, white, and 2 shades of gray.
Oh, 4 bits. Until 2 bits. You're right. 2 bits. Okay, yeah.
Yeah, so
IBM PC had 2 bits of color: white, black, and red and blue.
Yeah.
Fine. Yeah.
So there was like a ton of graphics they had to compress for the game, and a guy just went a video of several decompression strategies, and the video was pretty good. And just like all these decompression strategies you guys are talking about reminded me of it. So I threw it in the Google documents.
Okay. I mean, I lived in that era. I did graphics with encodings on the bitmaps and shit like that. That was part of the game writing.
It's very fun video. It's very fun strategy.
The first set of games that I did for money, I had to do my own Bessenheimer line algorithms because there weren't any such libraries lying around amongst everything else. Actually, at recognition equipment, when we had to do complex bitmaps, we're doing PostScript for complex bitmaps. The first laser printer, they had a very, very early laser printer predating Apple's by a fair number of years. And you had a bit slice computer that turned the laser on and off as it swept a line, and it had a hard time bound on how long it would take to do the line, and you had a hard bound on how many bits you could jam in. So you strangely compressed everything down to transitions from on or off for the laser, and then on the tick boundary for the line sweep, you had to jam in the next line set of bits for telling the laser what to do. And yeah, it was a variation of run length encoding done by a bit slice computer. Sorry, I'm reminiscing now. It's just like a good, that. All right, why did we get on this anyhow? Oh, here's your Pokemon graphics. Decompressing Pokemon Spike graphics. Yeah. Oh, it's a video too. Oh, that looks good though. Fine. All right, everyone's being really quiet here. We're gonna call it early if we're all gonna be done. I'll go hack AA code or pay my taxes, whichever comes first.
Wasn't tax day like a week ago or something?
Santa Cruz Mountain disaster. We got a 6-month to file taxes.
Oh.
So I don't have to file them yet. I want to file them. I don't have to.
So let's see. Well, so I mean, I'm working on intermediate representations. I'm trying to figure out the best one. So
I might be biased on that.
yeah. No. I mean, I've been carefully reading everything besides Sea of Nodes because I know if I ask you about it, I'll get an earful. So
I have an opinion too.
let's see. I mean, so far I've looked at continuation passing style, and then a normal form, and now I'm reading the SSA book, which is I don't know.
Your SSA will lead you down to the sea of nodes, but you'll go through tuples and quads first. I did quads because that's what was the tech at the time, and that turned into SSA on quads, which was hardly better than quads, but it was better. And then in grad school, I screwed with CPS style continuation passing. And I want to say we looked at a normal for a little while, and I fooled around with them, and it's like they never got me down to the low level, but they did interesting things for high level functional programming. But I couldn't generate optimized assembly or register allocate and things like that. Now these days maybe you can, but there was definitely a big gap from CPS down to what I wanted to generate code, or I would call it a big gap. There's definitely a gap there. Like you could definitely go CPS first and then turn around and flip again to go from CPS to I'm going to register allocate on these machine instructions. I wouldn't attempt CPS register allocation on a CPS style directly. I think you'd be causing yourself a lot of trouble, or you'd end up rewriting the IR effectively anyhow to get the representation you need to do register allocation. Fine.
Okay. Yeah, I don't know. I mean, the one I like so far is called Sequent Core. So it's based on like the sequent calculus, which is like this logic formalism that's two-sided, and so you have a value is like something on the right side, and continuation is something on the left side, and then you have a cut operation which combines them, and when you do that, you get like this abstract machine takes a value and a continuation and reduces it.
I highly recommend that you do an implementation of the simplest possible language with your IR of choice and look.
Oh yeah, no. So like that's what I spent a long time, like a year or two ago, implementing was the sequent calculus reduction stuff. And it's,
this is where you come to finding out why these IRs are good or bad and for what they're good or bad at.
yeah.
So
eventually you may also end up with an IR for your language, something on the higher level, because note that we have been talking about very low level code generation IRs that are mostly for the backend, maybe for the middle end. I mean, CPS, ANF, and even C of nodes are generally for an optimizing the backend of the compiler. But if you would like to have something for the language like Swift, maybe you would like to do high level optimizations of collections, data structures, and the composable algorithms, and well, abstractions in your language directly, then you may need to have a hierarchy of intermediate representations that mirrors the tasks that you want to perform.
I can do a fair number of good things with Sea of Nodes on composing functions, but I can't do conveniently large data structure shape manipulations where you change a collection or you change how you access a collection directly in Sea of Nodes, unless I start putting in nodes that are the whole collection, and then I just have an IR.
And to some extent, it's not just about making it possible, but also about making it easy For example, if you have an IR level that is specialized for loops, you can do loop fusion in one-liner. I have literally seen it done in the IRE, which is an MLIR-based compiler using a fine dialect for that. So it's good to have a task-specific IR, kind of like the Unix philosophy of a tool that does its job well. That makes it very, very simple to do what you want to accomplish.
Yeah.
So I never looked into, okay, I looked into IRs, but I never really understood how other languages do it. Every time I looked, it was just not intuitive to me. And then what I end up doing end up being fast. So I just never looked at it like in more detail what other people did. I don't know if I should explain how I did it and you guys tell me what other people do, or if you just want to summarize how other IR systems work. But I just never understood like why other people do it the way they do.
So I looked at some of your talks earlier, and it smells to me like you have either a collection of tuples or an AST with collections of tuples floating around.
Yeah, it's essentially what I did. Yeah.
Okay, that's a well understood technology. It has an obvious limitation in that it's very poor at doing optimizations, especially at the low level. It can be okay doing optimizations like function inlining and some kind of loop transformations are reasonable. Things that look like common sub-expression elimination do not play well in that kind of a space. Partial redundancy elimination, loop invariant code motion. There's a bunch of things that kind of suck on ASTs. Anything doing def use chains suck on an AST. So that's the reason these other other IRs exist, is to help with this other side of life.
So most of the
AST sucks.
Most of the IRs are because a compiler would want to apply optimizations to them.
Yeah, yeah. No, if you're literally just dumping code in and out, I would, then ASTs are fine. You could even go less. I have certainly had compilers that went from source code to machine code in one pass with nothing in between. They did a lousy job of code generation. They did it super fast.
Yeah, so that's kind of how my IR ended up being, because I knew I was going to pass it on to LLVM and they're going to do it the way they do it. And I was pretty sure I was going to do TCC because I figured that maybe I would want something faster. And if not TCC, my own thing. And so I just had a really high level one where I could just dump code in and out really fast.
Yeah.
And be very easy to generate like debug information. And it ended up working. So I just stayed with it.
No, that's a fine choice. There are plenty of folks who dump to C and then ask a C compiler to finish the job. And if you keep your semantics close to C, the C compiler will grok what you're doing and do a good job spitting out the back end. Like the JVM bytecodes, no C compiler did what a bytecode needed to do for threading model things, for garbage collection, pointer tracking, and a couple other issues. So I couldn't directly go to a C compiler. Also, going through a C compiler was just slower than doing the parse myself.
Yeah.
So
yeah, I kind of wonder how fast I could go, but it's like pointless. Like I got the debugging information from TCC. Don't need anything more.
Right, there's a lot of work there, but there's a performance gain on the code quality, and the code quality over time, like the ratio between how long to compile versus how fast the encode runs. And those trade-offs vary according to what you do. As soon as you add layers behind you, life got easier and generally slower for the code quality that you got out.
I didn't try to merge my IR, but I did I put everything in one large compile unit and just headed off to LLVM to optimize, because I just noticed that LLVM optimizes better if everything's just in one big file. And it's a little strange to me, but whatever.
No. I watched the Julia folks use LLVM for backend, and they're jitting code. So they hand LLVM lots of little code chunks as they decide it's time to compile. And LLVM has no runtime. It has no understanding for runtime. So it doesn't know how to cross call between separately jitted units. So all the cross calls are the worst, most expensive possible cross call, and the units are small. So you cross call a lot. And they're all, function indirect calls, and your branch target buffer totally drowns, and everyone's a BDD miss, so that's 30 clocks to cross call anything, and they get all kinds of horrible performance compared to Java because they're using LLVM with small chunks. And I know Arthur's not here, but he spent a long time trying to teach LLVM, both profiling data that Java has and also how to cross call between separate compilation units. And I don't know, he'd have to tell you the whole story, but I know he's made it work somehow, but they worked a long time at it. And the Julia
that
code that I
doesn't-
looked at did not.
That doesn't sound fun.
He said he spent 6 man years at it, or 6 years at it, maybe 6 years. He's been there a long time. And I would have said 6 years of hacking on C2 would have gotten you as much or more. I mean, 6 years to catch up to C2 using LLVM. And I said, you could have spent 6 years on C2. But he's not here. I don't want to hassle him now because it's not fair, but that's the obvious counter.
I don't even know why you would want to JIT code instead of just compile everything.
Oh, why you wanted to JIT it? Because you don't know. The common answer for Java was, I started this program. I loaded some code over the web. Now I want that code to run as fast as the code I just loaded up and ran from the get-go. But I didn't have it when I compiled the code from the get-go, so I couldn't have compiled it then. So I compiled it and I got it.
Debuggers, remember that you may want to use a debugger at some point. And for example, in debugger called LLDB, that's the LVM debugger, if user wants to evaluate C++ expression, that expression is going to have to be JITed. So LLDB had to implement a JIT compiler for C++. That's how it works today.
For a debugger. For debugger expressions. Yeah, right. Okay. Yep. I mean, I know that like IntelliJ hands those Java expressions back to the JVM. I assume he wraps them and the JVM does something.
So there is no magic. If you want to JIT compile an expression in the debugger, you're gonna need a JIT compiler. No magic.
I didn't think about that one. Yeah.
So I just figured GDB and both. Or go ahead.
The other piece of that one is the JVM does a lot of low-cost profiling. All the profiling in the world that you can do where the cost of the profiling is like not really measurable, it's under 1%. That in turn leads to a whole lot of optimizations that LLVM can't do well because it doesn't have profile data, and the JVM does. So he runs the code under an interpreter and gets base profiles. He runs it under a C1 and gets much better profiles, and then C2 has profile-directed optimization, profile-directed feedback, and generates better code than LLVM does at much faster, lower cost because he's got high quality profile data.
Every time I'm in here, I feel like trying to see how fast I can make an optimizer. Like I'm certain I can beat GCC and Clang.
Yeah, what I'm hearing you say is how fast can I compile code of low quality? So how fast can I turn code into something that I can execute, but the execution may not be all that high quality. And you've been doing shit like only doing array stores or array loads or whatever. That's all. I want to say that's like cheaty, you know. Like normal code really isn't giant megabytes of only array loads.
Yeah. But the thing is, I had to.
Also, are you measuring your compilation time with TCC?
Yeah, I measured.
Okay, one important point right there. TCC, I may be wrong about it, but I once recalled that TCC generates code that is slower than GCC at 0.0. So if you are able to generate fast code with TCC, you may want to choose a different comparison target.
Well, you have to add in a test of how fast your code executes, and then you need code that does something other than just array stores or array loads.
Okay, I have a feeling we're talking about 3 things at the same time.
Yeah.
So testing my own code, the array stuff is just because like I know that a million array assigns is going to be slower than a million lines of typical code. So I figure if I could do like whatever speed at a million times, like if I could do 3 million per second, real code I can probably do 3 million per second because they have spaces, comments, and all that.
You still want to do a variety of things. And in particular, if you're only running one code path through your compiler, the x86 will all start to predict and prefetch and blah, blah, blah. And it'll just run faster than it would if you had a mix of things going on. So if the mix of things is faster than all array stores, then, you know, you look even better. But it looks more realistic because it's a mix of things.
Yeah, I wasn't really too concerned of like how fast real code would compile. I just want to know that it can potentially compile that fast because like all the compilers are going to have the same problem as I'm going to have. So it's not like I'm going to like have really bad problems in one path. Like I'm kind of doubting that, but I guess I'm going to eventually find out. I'm not too worried
Well,
about it. at the
but
moment.
think about the entire workflow. I understand that one of your points is that you want to have fast compilation time for developer productivity, right? Because you want
Yes.
the developer to be able to compile the code fast. But the reason you want that probably is that the developer working on their code can iterate faster. And iterating faster, it may mean they may want to run their program from time to time and check whether it works. And if you compile to something that is slower than GCC at 0.0, which you may be doing with TCC, the iteration time slowdown may be so much that it doesn't matter if you compile 10 million lines per second, because it's going to be too slow to run the resulting program. So you have to balance these two trade-offs somehow.
Has that been a problem for anyone? Because I
To
never
my
heard of someone saying.
understanding, it's worse than GCC at 0.0. And yes, C++ has a big problem with debugging code without optimizations or with optimizations. With optimizations, the debugger jumps around because the information is not preserved. Without optimization, it's sometimes too slow to be practical, especially in interactive applications like game development.
Could you go a little bit more into that? Because from what I understand, the only time that problem happens is if you're writing something like a game engine where only one file has to be really fast, and then the rest can you can have all sorts of asserts executed, and it's just fine. So I'm not sure
for
exactly
a
the
game, it
situation.
would be running at slideshow speed. So you would no longer be able to debug the actual gameplay because it would be too slow to be practical.
But what's the use case? Like, what's the workload?
I have a big program. It does lots and lots and lots of things. I need it to run a while before I get to a point where I'm starting to hit the interesting part to debug. The run a while is part of my dev cycle. I want that to be fast. If that's 10 times slower because I'm basically interpreting, instead of running JITted code, that goes right to my bottom line of how fast the compile edit debug cycle is.
You know what this actually sounds like? It sounds like you guys are trying to convince me to do something like what Java does. You're going to be able to run optimized code and then fall back into debug code when you want to debug. But that sounds really hard, and Clang and LLVM doesn't support that. So it sounds like a lot of work to do if I want to do something like that.
That you should or you shouldn't in your own language. I'm saying part of my workflow is I'm running optimized code on things that would take tens of seconds to minutes. And then I'm switching to the debugger to go debug. And in the land of Hotspot, when I'm doing this in C code, that issue would show up from time to time. And then we would do weird, crazy shit. Like we optimized everything except a couple of modules because we need these modules so we could debug. But the rest of the VM, we would have to go hack or make files and say -O on the 90% and -G on the 10% and blah, blah, blah. And you screw around.
10 minutes to get 10 minutes to get to the part where you can reproduce the bug, because that sounds like a long time to reproduce a bug.
Not on anybody's big long running server apps. Yeah.
How many different things do you have to put together to do just in time? Not necessarily a excellent optimization, but at least to get the profiling in place and just to be able to say, this is JITted, this is deoptimized, back and forth to get a debugger.
I mean, I can tell you what Hotspot does, and you can decide that's more or less than, I don't know, how many things are in place. You have a compiler. It's going to spit code into memory, not to a disk file. You have a low tier execution path that you're going to debug with. That's the interpreter for Java, but it could be any number of low tier things. You have some debuggable path. You have some place where the debuggable path will also be the normal execution path until JITted code. And when he decides to JIT, he has some triggers. So the debuggable path counts. He says, I've seen this method once, twice, 10,000 times. I go call the JIT in the background. That's a thread launch but I could do that in the current thread if I wanted, but I could thread launch it. And the thread pool picks up the JIT and the method target starts to go. And part of that is he has to make an intelligent decision about what he's going to JIT, but leave that aside. He JITs something and comes up with a new alternative path for some execution point. Back in the slow version of debuggable, when you come around to that place where you have a choice of doing it the slow way or the new fast way, you jump to the fast path, and away you go in the fast path. So there's some handoffs between interpreted and JITted, or JITted from tier 1 to tier 2, or tier 0, 1, 2, whatever you want to do there. And then the fast path runs fast until somebody says, hey, I want to stop. So the fast path has to have a wait to run back to the virtual machine's execution model. For Java, that's a safe point and some bytecode point, but in C would be code points or sequence points. You test periodically, and you want the test to be cheap, so you do some sense, but in the optimized path, you can make the test really cheap, fine. So you do some cheap test, and then every now and then it says no, and you stop running the fast path, and you jump to usually an unwind handler that cleans your stack up and then puts it back into the correct format for the slow execution model, and then you're back in the slow mode. Slow mode hooks into the debugger and says, hey, the debugger wanted me to stop, do one bytecode and stop, do one sequence point, stop, do one sequence point, stop, or whatever it's going to be, right? And then when you're done debugging, the slow guy says, I'm going to run no stopping in slow mode until I come around to the next periodic jump to a fast path, and then I jump to a fast path. So you need a slow path, you need a fast path, you need the jitter, you need the transitions from one to the other, you need the ways to stop in the debugger at the slow or the fast.
Will this skeleton be in AA before you bring out the big guns?
Probably it'll come in pretty early. I mean, this is one of my goals is to have a runtime that lets me support JITted code, profile directed JITted code, and also full debugging, just like Java does. So that's a plan. When it happens when it happens.
So does this mean the debugger has a conditional variable, or do you write something in your code, compile it, and then execute?
I'm sorry, say it again.
So when you want to debug, if you want the code to enter the debugging state and not be so fast, like it has to know that at this point in time, I gotta switch back to the debugger.
Mm-hmm.
Does the debugger tell your virtual machine that? And is it a conditional variable, or is it something like what I do in C++, where I actually have the code in, I actually compile the code, like saying this conditional do a breakpoint right here?
Yeah, it's closer to the breakpoint. So the fast code in hotspot of a bunch of varieties, a lot of folks do the same way too. You test a bit, and you test it rare enough that it's cheap to test. You do it often enough, you don't have to wait long for it to come around. So once for every loop back edge, or unroll and jam, it's once for every in loop back edges. Once for every function call in case you're recursive and you're infinitely recursive and you have to catch them there, whatever. There's periods where you do it. The check looks like load a ThreadLocal storage register, load a word from that ThreadLocal storage, test the word for nil or not. The load is almost always cache hitting because you do it every 1,000 clocks or something like that, or 1,000 ops, something like that. And the branch is highly predictable. You never stop at a breakpoint. So it's 1 clock cycle per 1,000, 0.1%. You can't measure. It's too cheap to measure. You don't care.
It sounds like the debugger sets the bits, and you could just write it however you feel like in the debugger.
There's
yeah, that sounds pretty good.
It's not the debugger per se. There's handoffs because a lot of people stop the running threads in a JVM. So Mark was on. We talked about bias locking. GC will stop usually 3 or 4 different reasons to say crawl your stack, flip your stack roots, do whatever, count locks, or profile yourself. So at Azul, we had 20 odd reasons that we would do something on a stack that we would stop you at. Fine, for whatever reason, stack and threads stopping at a safe point have all their stack state in their L1 caches. So for them to do a self-service task is the fastest possible way. So if one thread wanted to ask another thread a question like, give me your current stack trace because I'm profiling you, the thread who's running does his own stack trace because it's way the hell cheaper for him.
It's a little similar to implementing dynamic of deoptimization and on stack replacement in the JIT compiler, and you can actually do that in C++ too. There has been a relatively recent article that does pretty much just that from 2019. I posted this above. So the idea is you compile 2 versions of the code. You compile optimized version and you compile unoptimized version with debugging information, and that your debugger at debugging time does pretty much the equivalent of dynamic of deoptimization and replaces the optimized function with the optimized function.
So this paper from Urs Hoetzel, Craig, and David Unger, that was the lead-in to deopt at Sun. That was the driving force. They're like Urs and David were definitely at Sun. I think Craig was still a grad student, and I came in sometime later, but they had already had a theory of how that was going to work, and I made it go for C2. And then over the years, we dropped the cost to the test for deopt and how all that worked. We never made the debugger have to rewrite the stack though. The runtime just rewrites the stack because he has other reasons he's going to deopt. It has nothing to do with debugger. So
if you already have a JIT friendly with a runtime, then that's you're done. You're pretty much done. But for something like that is compiled to machine code, you may have to do a bit more work.
Oh, okay. Yeah, okay. Yeah. The runtime did the unwind.
But the idea builds on the exact same principles. So yeah.
Right. There's no new principle other than somebody unwound the fucking stack, and now you could go forward in the debugger step by step, or just when the debugger was done, you ran forward till the next time you hit the code entry point for the fast code. And the slow guy can test for the fast point entry all the time because he's already slow, and a little more slow doesn't matter to him.
Okay, so for my situation, I'm using native code and not just in time. So is there something I should read? Like, should I be reading about save points, or is it something, or is
Look into the dynamic deoptimization and on-stack replacement first, and then you can look at this debug opt paper, debugging fully optimized natively compiled programs using multi-stage instrumentation, which applies those classic ideas, but to natively compiled code, in this case, C++.
Are both of those papers?
He put links on the chat. Get them in the docs. Or you did them in the docs too?
Already done.
Yeah, okay.
Okay, yeah, I'll look into those.
Yeah.
Yeah, I was just wondering if it's obvious enough that I could just think about the problem and have a fairly decent solution. But yeah, I'll read those papers.
The one thing that C2 does that I couldn't get the C compilers at the time to do was he'll preserve the Java execution state. So when the flip to the debugger happens, he has all the state at these save points. And then preserving that data costs you something in the optimized code. So the save points were rare, and then did things in the optimizer to make it cheap to record all this data. Like, you have a bunch of dead variables you're tracking. The compiler knows they're dead. The interpreter does not know they're dead. The interpreter and the Java virtual machine architected state thinks they're alive, and you should be able to inspect them in the debugger. He has to do something with them. He doesn't want to compute them because they're dead from his point of view. So you have to tell him that he has to compute them, and he's going to burn some cycles. Maybe he just spills them to the stack as fast as he can, gets that register free for something useful. And only on the debug path where you bail out and go deop the stack do you go reconstitute these values. So reconstitute might mean I did escape analysis, I exploded the object into registers, I never allocated. If I go to the debugger, there's an actual object. I have to go allocate an object and then stuff it with all its fields from register values. So there's a bunch of unwind things you do that you unwind in the optimizer. The optimizer is the best guy to do that unwind. You need to teach the optimizer, here is what I do if I take this path, and then I model that as here's an extremely low frequency path to a thing that reads and writes all the virtual machine state. And because it's extremely low frequency, the instruction selector and scheduler and shit moved all the repair and recovery shit into these side paths. And the register allocator spilled there and kept the hot path fairly well clean. So the cost of save points is usually pretty low.
I'm definitely not going to teach the LLVM's optimizers anything.
If you can hand it profile feedback, or if you can hand it frequencies for branches, expected frequencies on branches, that'll go some ways. I expect this debug point is never taken, essentially zerally taken. Now,
C++
it's not dead.
C++ has a built-in expect where you hand it like 0, 1, or some period if it's like how likely it is to be taken or not taken.
Right.
That could work, and I used it a few places, but I found that the branch predictor does a better job.
Here's the deal with branch predictors. If you make them predict too many times, they'll run out of their cache. It's a fixed hardware cache, and they'll quit predicting. So
also, built-in expect is not for branch prediction at all. It never has been. It's only for code layout control. if you have an if statement, for example, if condition, then basic block A, else basic block B, then the built-in expect and how likely the branch is tells you which should go first, because you want the one that is going to be more likely to be laid out right next to the code, so it's fetching the instruction cache and the CPU can execute it swiftly.
No, there's a key difference here. The branches that are not taken are default fall through, and branches that are taken default backwards. If you think you have a safe point or debug point that will essentially never be taken unless I breakpoint at that point, it's going to fall through. Or you want it to line up fall through. So you want to set the expect prediction so that the fall through path is a default. Because it's now a default, the x86 will statically predict it correctly. Because he's statically predicting he won't touch his branch table, his prediction tables. And his prediction table will not be polluted with debug points. If you do it the wrong way, every debug point on the planet will have to run through the prediction table, and you'll have way more of them than the size of the table, and the prediction table will get swamped and will quit predicting.
Right. But nowadays, the major performance effect is going to be from the instruction cache. Although the end effect is what you want in any way, so you still want the code to be out of line. However, Cliff, I know that because I have seen that the reverse engineering for the Intel Haswell, and since Intel Haswell, which has been a few years ago, there is no more default prediction in the branch predictor in any of the x86 CPUs. So
Okay.
in part, so there is no default state that you care about anymore.
I
What
hear
you care about mostly, since Haswell, is the code layout. Although in the end, we want the same thing, because at the end of the day, you still want the code to be out of your way.
Yes,
That's pretty much the point. And
the code needs to be away. That's also true, because that's iCache efficiency. It's how much hot code is in your cache and how much cold code is in your cache. I find it hard to believe there is no static prediction, because if you...
Well, it's hardly relevant. It's for most of the spec benchmarks, which are small, tiny applications compared to today's workloads. Even for those tiny spec benchmarks, there was no benchmark where it mattered. Someone basically ran the comparison, training different, warming up the state of the branch predictor to make it predict a given default state at random. And there was no impact. So basically, you can do what you want, but it's not going to have any performance impact.
Well, I'm interested to see not that test, but one that says I just took all the branches and inverted my statement, and see if he and used a moderately large app and see if he doesn't have issues where his branch target buffer just blows out. And then you get...
It's going to be very hard to make such a test, of course, without the code layout effect. And the code layout effect is going to chill it. That's going to be important.
Yeah, right. You're going to get both at the same time. Maybe. Oh, Leo, it was static branch prediction on x86 was what I would start with. I don't know what they called it now, and I don't know what Haswell did. So Matt could totally be spot on here.
Yeah, I was just looking at the x86 instructions. So you're saying that what I want to do is make it so checking if I want to debug is false. So I never take the jump and I just roll right through.
Roll forward,
I was just trying to remember how many jumps instructions there are, because I mostly just see jump subroutine or call and jump, but it looks like there's a lot of jump
if you
less
look
than
at
and all that.
a large complicated app, you're going to get a lot of jumps. If you look at hotspot generated code, there's a lot of safety checks, and the typical basic block length is 5 ops. So every 5th instruction is a branch, and nearly all of them are highly statically predictable. And you don't want to blow out the dynamic prediction table. And then Matt says it makes no difference now.
Well, it makes difference for the code layout. It makes difference for the code layout.
Yeah, it makes difference for the code layout. Yeah,
huge difference.
Yeah, and then fall through, of course, does the right thing for code layout, and jumping does the wrong thing typically. So,
and you can do a lot of things on your language too. If your language has exceptions, for example, then you can put the exceptional path as the unlikely path, so it also is not on the way.
I have no idea how to do that because I only ever use built-in expect on if statements. But I do know that when I did that on the if statements, whatever is unlikely would be what is jumped to, and that's the only reason why I did it. It's because I just want that code to be away. So yeah, I found built-in expect very useful.
Was it you were able to tell a difference in performance or not?
You know what? I can't even remember because there was so much that affected the performance and it was so noisy because like the kernel was taking like 8 or 9% of the total time.
Oh, that was your giant alloc. Well, I claim that was some combination of like.
Oh, map populate ruined everything, but after getting rid of that, like I already had all the built-in expects in the code, so I didn't want to yank them out just to see if it went slower. But it was just too noisy, like all the time. Like it would just fluctuate like 60 milliseconds every run. It's so hard to tell.
Yeah.
I would measure that if I were you, because there is a history there. So Fortran, which is one of the first programming languages, had a very early on, its very early version, I don't know if it was 50s or 60s, a frequency statement, which allowed the programmer to tell that the condition of an if is going to be frequent. So pretty much what we would say likely today. It had to be eventually taken out because it was found that most programmers who were using this exactly in the opposite way. So what they were guessing to be likely or was unlikely, what they were guessing to be unlikely was likely, and they never profiled their code again after putting it in the frequency statement. So there is a long history of people getting this wrong. So I would be careful if I were you, and I would measure and continue measuring in continuous integration system, for example, whether this prediction has been correct, especially if it's
Oh.
anything different than the obvious error handling.
I got a funny story about this. So I ran my code coverage and I saw an if statement that was about 50-50. And the if statements right before it always set the condition to true. And I'm like, this is only going to take me 15 seconds to make a copy of and to move it up. I'm going to spend the 15 seconds to do it. And then I ran it and I'm like, should this be faster or the same? I'm like, it might be the same, but I just wanted to like see if it actually was. And it was the same. So I hit undo, looked at the assembly because that would take much more than 15 seconds. And it turns out the optimizer already did for me, but I still thought it was like kind of fun. And I still use the coverage data to help me figure out if something's likely or not. And I end up moving one other if, and I think that was a little bit faster, but it's really hard to tell if something's 1 millisecond faster or not because it's just 1 millisecond.
Sorry, I'm reading x86. Yeah, yes, Levo, you were talking and you quit suddenly. If you
Well,
could hear
I
me.
mean, I still have to wonder, like, how much of what you're measuring is noise? Because
Oh,
I
a
mean,
ton, a
stabilizer,
ton.
I mean, stabilizer, you know, they showed that if you just randomize the order of the blocks in the program, then you get like a 20% difference. So, you know, I mean, yes, you can reorder them, but you know, I don't know if it actually, I mean, it's like, you know, is it worth it when the compiler is just going to reorder them again and undo what you're doing? So
Yeah, that's why I went to coverage, and that's why I just didn't really care because it's only like going to be 1 millisecond, and who cares about 1 millisecond? But yeah,
well, I
it's
mean, you
definitely a
say
lot of
that, and then
noise.
you spent like you looked at the assembly, you actually did
No,
it.
no, that was okay. Well, that one change was only 15 seconds, and the other optimizations I did would it's actually 3.1 million lines that I do, but I just say 3 million because it's easier. But most of the time when I actually like save and like when I do something and I got results, usually I get like 15 plus milliseconds, which is like half like 50,000 lines. So it's usually not nothing, But yeah, I think I optimize enough, and it's only when I get inspired by something that I try to optimize. But yeah, nothing inspired me lately. I just, after the map populate, it's just everything was pretty clean, so I looked into it again, and then I didn't see anything that looked like it could be like a good saving. So like I just left it out there. No other targets, low hanging fruits.
I mean, they aren't low hanging when you have to invest like a few minutes for each optimization.
A few minutes for 50K is pretty good in my opinion. But only when it works. A lot of times it didn't work.
Hmm.
It's really hard to tell if something's going to have a good payoff.
I don't know. I mean, it's just like, I mean, you're probably gonna have to make major changes so when you implement like the standard library and stuff. I don't know. I think it's
I'm
premature effort.
reading somebody's discussion on Haswell branch predictor, and they basically came around and said, we actually just don't predict, we just go forwards always, or the prediction is fall through every time.
Yeah, I couldn't prefer that. Sounds good to me. I still can't believe I have to manually do a loop unrolling.
Oh, a C compiler's not gonna unroll for you?
It does, but not when you need it.
TCC, I can imagine not, but I would have guessed LLVM would unroll. But
Because in my situation, I had a loop and I was testing. I was testing by using trailing zero. I forget what it's called. The trailing zero instruction. Yeah, so I was using that
Counting
to figure out
zeros.
my array index, and it's since it can do two in parallel with Haswell, it just didn't want to emit that code. It just did one at a time, and then I just forced it to do two at a time, and it worked. It was like faster, and I just thought, well, why didn't it do it itself? But it just didn't.
No profile data. I don't know. I don't know.
Yeah.
I certainly, when doing like certain ML kernels at H2O, I wouldn't let the JIT guess. I would just hand unroll and force the issue. Not very often, but a few times.
It might be because I'm using SIMD instructions and it just throws its hands up in the air. And it was also GCC because GCC got me faster code than Clang. But like, yeah, I wasn't too happy. And that's why earlier I was saying that maybe I can beat the Clang and GCC in optimization. But that's because I had to like profile and change my code so many times that I figure if I just implement that and what I already know, I might be able to do as good, maybe a little bit better, but I don't know. This talking here just makes me want to try it every single week.
All right. We got anything else going on? I'm gonna call it quits. There's a ton of reading material though, that's for sure. All right. I want to declare victory.
Yeah, I mean, we have a guest next week, right?
And we have a guest next week. Is it 5? Yes, we have a guest next week. Talking about Jamie, he's the new guy on Discord, Jamie Willis, talking about parser combinators as a way to do recursive descent using Haskell to define parser combinators. And he says he won't say the word monad or functor because it'll scare everyone off. So
Right. He'll say applicative because
oh, excellent. Fine.
I still feel like I need to read up to understand next week.
I think if you Google, somebody threw the link, I thought I threw the link out. There's some Google thing you can find him really quick and then go look at what he did. And there was some YouTube video of a presentation he made, and there's papers, and some of it
I'm
made
probably
sense, some of it did
I
not, but
can
only kind of loose sense because I don't read Haskell well.
I can probably look up the terms while he's saying it, or look up
Yeah, use his
Haskell
name
terms.
and partial combinator. I think you'll get something really quick.
Okay, yeah, maybe.
When we're speaking of references, so I mean, you said like you were using it was like SSA on quadrahedral something, right?
Quads.
Quads.
Old school compiler IR. That's actually, I mean, I think LLVM still uses it. It's not uncommon. That's just an op code. A single IR node has an op code, a couple of inputs, generally 1 to 2, but sometimes they need a couple, and an output. And so quad is because I had an add, a left hand, a right hand, and a result instruction, a register. So this is virtual register, virtual register, virtual register, sorry, virtual, it's an opcode, virtual register left, virtual register right, virtual register result. 4 things, that's a quad. You put a bunch of them in a linked list and you call it a basic block. You put a basic block in a classic graph, you got a control flow graph of basic blocks of instructions. This technology has been around since the 50s and 60s and is still commonly used. If you're not doing SSA, if you're not doing graph-based IRs or CPS or a normal form, things like that, you're probably doing some version of quads.
Okay, yeah, like I mean, the stuff I've read, I think that's called like 3 address code. So,
3 address, I just said, left hand, right hand result. Yep.
right, right.
But you need an
I
opcode.
haven't heard
That's
the
your
name
fourth.
quads, so
And that's the quad. Yeah.
3 address is what I do with my my IR.
Yeah, like I said, extremely common.
all right.
And the
Well,
only
I'm lumping that under SSA
nodes
representation.
was,
That's-
sorry, I couldn't hear you.
I said I was lumping the 3 address code under SSA because everyone's switched from using 3 address to using SSA 3 address.
Yes. Okay. Right. If you don't have SSA, there are virtual registers. If you have SSA, there are virtual registers with unique names. If you replace unique names with pointers to the defining point, it's sea of nodes. That's kind of the connection between them.
Okay.
All right. Next week, we have a guest.
Bye, everyone.
Bye-bye.
Bye.